Hi, my name is Manish Gupta, and in this video, I'm going to talk about XML-CNN, which is basically a deep learning model for extreme multi-label text classification. So let's get started. Extreme multi-label text classification is the problem where you have input as a text document and you want to classify it into multiple possible categories or labels out of a very large set of labels. For example, given a Wikipedia page, you want to classify it into one of tens of thousands or probably hundreds of thousands of possible categories, right? So people have traditionally not been using deep learning models. They have been using label embedding based models, tree based models, one versus all classifiers, and so on. But this was the first time in some ways that these folks essentially tried to use deep learning models for this problem of extreme multi-label classification, specifically for text. The model is pretty simple if you think about it in today's world. They essentially use a CNN, as you see there. Each document, each word is actually represented in each word in every document is represented using pre-trained 300 dimensional glove vectors. You have a maximum size of m words per document. If the document is short, you pad to make sure that it has m different words, each represented using 300 dimensional vectors. This is followed by a convolutional layer, as you see here. The layer contains filters of different window sizes, 2, 4, and 8. Remember, this is being applied on a text matrix. Therefore, the width of the filter remains, um, remains the same as the size of the embedding, but then the height sort of changes in that senses. So the window size changes. Basically, it could be 2, 4, or 8. And the number of filters that are used or number of feature maps for each filter were like 128 for smaller data sets and 32 for larger data sets. Now, this overall leads to T different resulting feature maps. Now, T could be 128 into 3 or 32 into 3, depending on whether it is for large data sets or small data sets. But the idea is that it leads to T different feature maps, each of size M, right? So essentially, because there are M words, and for each of those words, you finally end up with some feature map. Now, you take this m-sized vector and you essentially divide it, split it into p different chunks, p as in parrot, so p different chunks, and then you do max pooling over each of those chunks. Therefore, effectively, this max pooling essentially, max pooling operation p actually actually results into a p-sized vector out of every m-sized vector. Now, since you have t such m-sized vectors, you end up with t such p-sized vectors after the max pooling is done. So that's that. And after you have, so this is basically called as the dynamic max pooling layer, which essentially takes m-sized vectors and gives you p-sized vectors by dividing the m-sized vector into p chunks. So essentially p different chunks. This entire size is m, and there are, in some ways, each of those chunk sizes m by p. And that gives you overall p different chunks. And then you take the max over those each of those chunks, and that gives you the p-sized vector. After that, you apply a fully connected layer to get a compact representation, and the last output layer is also a fully connected. So this fully connected layer for the compact representation hidden layer is of size 512. And then finally, you apply an output layer, which is of course also a dense layer, but with sigmoid activations and with a binary cross entropy loss. So the binary cross entropy loss is computed as follows, which is the standard definition of binary cross entropy loss. It's basically defined over all the points, data points, and over all the labels. And for each label, essentially, you are capturing, you're applying sigmoid over the predictions and then comparing it with respect to the actual ground truth label. The evaluation was done using the standard extreme classification metrics, precision at K, NDCG at K, which in turn also uses this discounted cumulative gain at K. Uh, of course, this is extreme classification setups, which basically means that the ground truth labels are 1 or 0, depending on whether the label is relevant to the text document, input text document or not. Therefore, precision at K is computed as 1 over K, and you look at the top ranked, top predicted labels, and you sort of, add a 1 if the top ranked label was also a ground truth label. Else you had a 0 to the overall computation, and that gives you the precision at K. Similarly, you compute DCG and NDCG at K. So how does XML CNN perform? They compare across 7 different methods. Using metrics like precision and NDCG. I've shown results here for precision. NDCG results are in the paper. And they also do comparisons over 6 different data sets of different sizes. So Amazon 12K with 12,000 labels, 670,000 labels, and 500,000 labels, and so on. As you can observe, they compare with various kinds of methods, one versus all kind of a method, label embeddings based methods, and also tree based methods. They also compare with other text classification methods, which were not really shown to perform or experimented with extreme classification setups. And they observe that XML CNN performs as the best or the second best method on most datasets. Specifically on one of these datasets, Wiki 500K, which has more than 2 million documents and 500,000 labels, XML CNN outperforms the second best method by up to 11.7 to 15.3% in precision at K. So essentially, if you look at the second best method, in which in this particular case, it turns out to be Sleek. It outperforms Sleek by 11.7% to 15.3% in precision at K, and also by 11.5% to 11.7% in NDCG at K, which is not shown here, but is there in the paper. Okay. Now, XML CNN actually introduced a few extra components on top of the traditional CNN method. For example, it had a binary cross-entropy loss. It actually brought in an extra bottleneck fully connected layer before the output softmax layer. And it also had this dynamic pooling layer instead of the max over time pooling layer. So and therefore, folks also did these ablation experiments. CNN-KIM is the standard CNN model, which basically takes the word embeddings, concatenates them across, across all words in the document, and then does T-convolution filters on top of that, does max over time pooling, followed by a fully connected layer with L softmax outputs. Right? So on top of that, they did these 3 additions. So they basically added BCE loss in V1. In V2, they actually added the extra bottleneck fully connected dense layer. In V3, which is their final XML CNN model, they also added the dynamic pooling layer rather than max over time pooling. And as you can observe from the results on these 3 different data sets, Eurlex, Wiki 30K, and Amazon 670K, across these matrix precision at 1, 2, and 3, you observe that as you keep adding these various components to CNN-KIM model, or the traditional CNN model, it gives you better precision values. Therefore, it sort of shows that each of the components that they added actually added quite some value, right? So in summary, in this video, I talked about XML CNN, which is one of the first models, deep learning models, which has been proposed for the extreme multi-class, multi-labeling, multi-class, a multi-label classification problem. Right? They had 3 main components. They basically introduced a dynamic max pooling layer, binary cross-entropy layer, and also a hidden bottleneck layer for obtaining better representations of documents and smaller model size. So that's it. And they basically showed over 6 different data sets comparing with the several state-of-the-art methods in 2017 that their method gives better precision in NDCG values across many of those data sets. That's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.